All right, so as you see, we have a visitor in the classroom today, so we should minimize profanity and maximize Batman puns. Uh, Christian worldview. All right, so quiz. We talked about shared memory versus message passing. When's it a good idea to use message passing?
Maybe send a pointer or one-way unidirectional information to another process.
Okay, keyword being there, one other process. Okay, we use message passing when we're only sending information to one or a relatively small number of additional processes, right? Okay, so the other side would be shared memory, kind of like our singletons, right? We talked about. So we throw everything up in one centralized place so that any interested processes can just grab the information up here rather than having to be the recipient. Last time we talked a little bit about mailboxes, right? Okay, rather than having to be the recipient of it. So message passing, communication between a single process, well, that would be kind of talking to yourself, but communication between two individual processes or a relatively small number of processes versus shared memory being communication between many processes. And in real life, in an operating system, we might start seeing that being, we might have information that needs to be available to processes that have not been born yet. So when they come into existence, they might need to check with what's going on to find out what they need to do next. Okay, and we're going to start talking, when we finish this chapter today, we'll start talking about threads. I already put up the slide set for chapter 4 in the on Blackboard, and then also I gave you another homework assignment. How did the homework assignment go? Too easy? Just right? Okay, because I gave you about 10 times more work on this next one. Okay. Next, the next chapter should actually go pretty quickly because we've already talked about threads quite a bit. So most of our discussion in chapter 4 is going to deal with kernel versus user threads, and we'll talk about that here in a few minutes. Let's kind of power through the rest of these dinosaurs. So in any case, a lot of the examples in here, and you probably saw it when you were doing your homework assignment, they kind of are comparing multiple operating systems and how threads and interprocess communication works on them, like POSIX stuff and how Windows does it versus Linux does it versus things like that. Relatively unimportant because operating systems are constantly changing, and at some point in time, we're going to kind of get to, oh, this is the right way of doing it. So, for example, you guys looked at remote procedure calls in your homework assignment, right? And what's the purpose of that? It's that RPC as opposed to local procedure calls. What's good about remote procedure calls in the world of interprocess communication?
Well, they had those mechanisms that would like stop duplicate messages. Many faults.
Okay, so they have some power tools built around them for protecting things that are common faults. All right, so would we say that in the old days of interprocess communication, it was very much a manual approach, right? We pick shared memory or we pick, let's see, did they talk about semaphores in the reading? Maybe not. Okay, that's just resource control. I'll throw that in somewhere. But punchline is that when we have to do it manually, not only are we dealing with whether we're throwing something in a mailbox or we're throwing something in shared memory that lots of people have access to, we also have to deal with the possible problems that run into that. Okay. We also have to externally to that write the logic on how that shared memory is used or how the mailbox should be used, how many people can access it at once, what do they do when they access it, do we limit control to it, things like that. Remote procedure calls, what do they give us that doesn't? Well, let's think about local procedure calls. So you're writing your Java program or your C# program and you write a function or a procedure. Okay, why do we write functions or procedures in our modern programming languages? What's the advantage of that rather than just throwing everything in main? Okay, certainly organization. What does that mean? So, I mean, so fine, your code looks a little blocky, right? Instead of having this giant monolithic main, we just kind of separate into little chunks, and that's just better. It's more organized. What's
Easier for other people to read.
okay? Fine, easier for people to read. Does it give us no other ability other than that?
I mean, that's kind of how humans problem solve the object-oriented piece of it.
So let's go back to a class like 250 or even 200 before that. What's the definition of a method? Okay, chunk of code that we can reuse. We write it once and call it over and over and over again, right? Okay, so it's not just for organization. If we have a monolithic main in our program and we write this little chunk of code here, and then we actually need that again later on, we have to copy that and paste it down here. That's certainly, we can say, bad programming practice, but it's also, not, if during the day you need to toast something multiple times, you don't buy 2 toasters. You use the same toaster twice, right? Okay, unless you're Nick, and probably he has some ghetto toaster that doesn't work that well, so he has to have a couple of toasters laying around because he's not sure which one's going to work today.
They're parts toasters.
Parts toasters. I'm going to have to go salvage a coil off the toaster so I can make my Eggo. All right, so punchline is reusable chunks of code is a power tool for us, right? Okay, and we do this in our normal programming languages. The book calls it a local procedure call as opposed to a remote procedure call, LPC versus RPC, right? You probably saw that in there, right, as you were reading through it, because they were probably introducing it from that perspective. But punchline is that we have remote procedure calls as a form of inter-process communication because it allows us to create an entire solution to communication in one place. What inputs do we need to make this work, and what outputs are we expecting from it? So rather than having to manage the whole communication process between 2 procedures and say, okay, well, I'm gonna send this piece of information to the shared memory. Then I'm gonna wait for you to go and read it and then mark this thing in my local mailbox, letting me know that you've read it so I can go back and read it here. So we have this whole little protocol that goes back and forth between these guys, right? So rather than manually doing that, where it's like a song and dance, we can now have a remote procedure call that has all of it packaged into one little fell swoop. We can just call that guy and he does his job and then notifies us when he's done. Okay? Having said that, are remote procedure calls popular? Sound great on paper, right? Just like distributed computing sounds great on paper. Well, distributed operating systems sounds great on paper. As you were reading through there, what did you find out about remote procedure calls in terms of their popularity? Seems like there's a whole lot of talk about shared memory and mailboxes and message passing and just kind of almost an afterthought thing with remote procedure calls, right? Why do you suspect that's the case? The book's always kind of focusing on these various libraries for things, like in the next section, and they're mentioning it in this section and the section before because we've been talking about threads a lot, but they're talking about P threads and POSIX threads and these various standardized libraries for things, right? Now, with remote procedure calls, is there a standard for that? Or does every operating system kind of have their own way of implementing it? Given the way I just staged that question, it's probably the latter. Okay? All right, so, and really actually, kind of an interesting thing, remote procedure calls was something that was originally put forward by Java, which is probably why it failed. All right? Java's greatest strength is also its greatest weakness. Right? Java's platform, its platform independence leads it to not have to organize things too much. Microsoft's greatest strength is the fact that you can get Visual Studio and everything's just packaged in there. Anything you want to do, there's probably a drop down in some hidden place inside of Visual Studio for it, right? You wanted to talk to SQL Server? Well, did Microsoft make it? Sure, no problem. Drop down, it just works. Java is a much more disjointed technology. The stuff doesn't talk to other things very easily. And Java's remote procedure call took a whole lot of setup in order to get it to work. And then what ended up happening is each operating system decided, you know what? this is a good idea. We'd like for stuff built into our operating system to be able to share information with other stuff built into our operating system. And remote procedure calls is a nice organized way of doing that. But we're going to have our own Sun Solaris way of doing this, or our own Microsoft Windows way of doing this, or Mac OS way of doing this, or Linux way of doing this, or BSD Unix way of doing this. All these different ways of solving the same problem, none of which are compatible with each other. Now, would you agree in real life, when we write user applications that might have processes that need to talk to other processes, one of our goals might be, unless there's a major advantage for something to run only on a single operating system, we might want to write it in such a way that's fairly generic. You know, we should be able to have a program that runs on Windows as well as runs on Mac as well as runs on Linux. Certainly user level, you know, when you start talking about video games, it goes a whole different story, right? Okay, but user level applications, the more things that we don't have to rewrite 30 times, the better. So are we going to use these proprietary technologies in there? Or are we going to use kind of the go-to things that are built into all those operating systems, even though they require more micromanagement? Probably the latter, right? So remote procedure calls ended up being a pipe dream that never became a reality, even today. Even today, they're only used in very special cases because they never actually went to a standard.
Do you think that should be a standard?
Well, certainly. I mean, you know, they're obviously a power tool. I mean, we haven't gone on, you know, when we talk about just writing programs, we haven't moved away from this idea of having methods to something different. Methods seem to be a nice, compact way of calling upon an ability. Here's the crap you need to solve that problem. Go do your crap and hand me back the answer. Kind of the perfect little solver, right? Okay, and certainly as we get into the next section and start talking about threads, now we can have a thread go and solve that little problem using remote procedure calls. So it certainly should be a standard. Okay, but it was because each operating system wrote it in their own little way, because it was a newer technology. When we look at a lot of this stuff, notice in the book we have a lot of old examples. So let's go back to one of our forking examples. Well, I mean, this is good enough, I guess. It's not a forking example, but you know, this example right here, this is old C code. So was this code likely for a bounded buffer? Was this likely written before Windows came out? Before the Mac OS came out? Before the operating system that runs on your Xbox came out? This is something probably from old Unix, right? One of the old operating systems. And you know what? They said, hey, this just works. Why fix it if it's not broken? So our modern operating systems just brought these implementations over. Even when we looked at the fork system call, okay, which came from Unix, and we looked at the Microsoft equivalent for, I think they pretty much just said, well, we're not going to call it fork because that's creepy to fork children. But at the end of the day, it's still solving the exact same problem, right? So they just changed the name a little bit, but the implementation of the hood is still written in C. It's still written using a fork system call. So if it's not broken, why fix it? Remote procedure calls didn't have that ability. We didn't have that advantage of having them around in the late, 60s. And now we can just drag them into our modern operating system and say, oh, well, this has been around forever and ever and ever, so let's just keep using it. We don't have that ability. And I don't think people care enough about operating systems at that level to make it a standard. All of us in here are operating system users, right? How many of you really, truly care? Do you sit around and think about how one process talks to another process? Do you care how convenient that is? As long as it works? Because realistically, a process call, a remote procedure call, this guy, is he any faster than doing it your homegrown ghetto way? By just having shared memory mailboxes and having little things to determine the cadence, who sends the message first, then this is what this guy sends, this is what this guy sends, and this guy reads this. Is the remote procedure call going to be any faster? Or is likely that remote procedure call written in terms of the things you could do on your own? Each operating system, what did they do? They said, okay, well, here's a good idea, here's a good way, here's a design pattern for how remote procedure calls should work in Solaris, or work in Windows, or work in Linux, or work in the Mac OS. Here's how we're going to do it. And they're always solving those problems in terms of the tools they already have available, right? What tools do they already have available? Shared memory, message passing. We talked last time, everything's done in terms of send and receives, but those send and receives are implemented in terms of either a mailbox or a shared memory section or something like that. But they're using the exact same tools to solve that problem as you could just solve on your own. So, is there really a speed advantage? Or might there even be a speed disadvantage? Is there probably some level of overhead associated with a remote procedure call? So are there aspects of our operating system that needs to be really, 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 really fast that we don't really care if it's done in some sort of fancy schmancy way, as long as it's really, really fast? You know, we translate this back to our video game world. Okay, those of you who are gamers, do we care if our games are fast, or do we really want them to be written in really nice, organized code under the hood? Would you want your so we'll take our Fallout 4, the current crappy game that just got released, right? All right, so do we want that? Do we care what that code looks like under the hood? Or do we want it to run fast? If we were promised it was really nice code, but we got a 30% decrease in performance, that would be good with us, right?
That's written by Bethesda, so they get around that stuff, right?
Isn't it going to, or isn't it not going to?
It's not going to.
Oh, so Bethesda's known to be garbage? Is that a true?
They're not known to be garbage. They're just like
Overly ambitious.
Yeah.
Like,
I don't know if this is on other platforms, but at least on PC, there's parts where like people's heads were sticking through various components and stuff.
That's like classic Bethesda. Like that's every game is like
Really?
bodies through stairs.
Yeah. So that's considered like they're
They usually figure it out.
within 6 or 7 years they kind of get it hammered out.
Yeah.
No, Fallout 3. Yeah, Fallout 3, I had to force to run on one core on my machine to get it to work.
Really?
Yeah,
That's weird.
Apparently, my system was too fast for the game.
Oh, I have some examples of that. This is before your time, but when I was a kid, a popular game in the arcade was Double Dragon.
What's an arcade?
Hey, what's an arcade, right? Okay, you remember Double Dragon? Josh? So I love Double Dragon.
They came out with a new one, Double Dragon Neon.
Really?
Yeah, it's pretty fun.
Oh, so I had Double Dragon, and first I played it in the arcade. There would be lines, people waiting in line for Double Dragon, and then we got it for our IBM DX2. Well, no, we had it for our IBM X86. Oh, it wasn't IBM, it was an Epson computer. This is when Epson made computers, not just printers. So we had an Epson computer. It was a X86, I think like 12 megahertz computer or something like that. And it was so cool. Double Dragon. Oh, I have it at home on my keyboard, and we got these joysticks, and it's like, it was awesome because having a joystick connected to a computer was like you had arrived. Was the punchline, all right? But a couple years later, when we got a 486 DX2 66 megahertz based computer, and we saw the true poor programming of that Double Dragon game. They must have timed when bosses came out and stuff like that based on like busy wait loops, because the game that was timed right before now ran at light speed. Okay, it was completely unplayable. Things were just flying on the screen. You couldn't even control your guy anymore. So we don't really care how the code's written under the hood until we care how the code's written under the hood, right? As long as it's serving its purpose today, we're good with that. But at the very least, could we agree that there are aspects of video games that we can all understand as users when there's lots of explosions happening on the screen, or in multiplayer games when there's a zillion people all in the system at the same place, crowded towns, that kind of stuff, that those are the times that we're most likely to experience like sluggishness, lag, or something like that, correct? So those are the parts of the game when we notice. If we're just running around doing something menial, we're not really going to notice if it's running at 600 frames a second or 32 frames a second, right? They're going to feel the same to us in the big scheme of things. All right, it's the slowdown that makes the difference. And this kind of connects, when we talk about kind of the grand ideas of computer science, this connects back to compilers. So we talk about low-level versus high-level languages, right? So we're all used to using high-level languages for writing all of our stuff. Okay, well, what's a high-level language? Java, C#, something like that. Well, what's an example of a low-level language? Assembly. All right, well, we'll look at assembly a little bit next semester in the 325 class. But we've seen it in here. We saw the Hello World program in assembly, right? Using those system calls with our registers. We looked at that not that long ago. Okay, so the idea is, would any of you want to write code in assembly? It's like, we don't want to write code in our high-level languages. Yeah, most efficient way. Well, shouldn't I talk directly to the CPU? Shouldn't I have a one-to-one relationship with the CPU? Why is it so one-sided? Why are you giving me these power tools? I should be able to just talk to the CPU on an equal playing field. But it's not efficient for a human being to do that because we have to be so verbose, right? We don't think that way. So why do low-level languages exist? Does a human being ever have to go and write assembly code? Okay. Why? Okay, well, we certainly aren't going to write in machine code. Okay, the zeros and ones we're going to fail at quick. All right, human beings, the 2-button keyboard does not work out well for us. All right, but now assembly code exists. Does it exist just for the sake of compilers? For compilers to turn our Java or our C# or whatever into the low-level language that knows how to talk right to the CPU?
Now, would you use it for like debugging, like to see where, like, what memory is being accessed, exactly like when, where to see like where something's being jumped to or something? Because I know that a lot of people use it for like the only time I've seen people like use like this like assembly code on like YouTube where it's like, here's how to unlock this program, and it's like, well, just change this to jump to this memory address, and now your program's unlocked, and you've got.
Okay, so we can use it for pirating software.
Right. Yeah.
All right, fair enough.
Use it for theft.
Okay, okay, perfect tool for theft. Yeah, makes sense. Okay, so yeah, Christian worldview. Bank that. So, all right, so that's more of a side effect, right? Now, would you agree if every one of our programs is ultimately going to be talking to the CPU, is ultimately going to be talking to this one resource, at some level, we need to talk to that resource on a one-to-one level, right? Whether it's us doing it or whether there's all sorts of mappings that happen between us and the CPU, at the end of the day, something is communicating with the CPU, telling the CPU to do this, then this, then this, then this, then this, in terms of the magic tricks that CPU knows how to do, right? At some point, that's happening. So at the very least, we can say that a low-level language like assembly exists for that reason. Okay? Now, we could say, well, maybe it only exists for the sake of compilers. What's the job of a compiler? A compiler converts a high-level language into a low-level language, right? So, well, we have to have the low-level language. We have to have this guy that has a one-to-one relationship with the CPU. Otherwise, we can never actually talk to the CPU, and then the human being is going to have to step in and talk to it directly. All right? So instead, we're going to let the human being go to Home Depot and get the power tools. And then as they're solving their problems, we're going to filter their solution through this compiler that's going to squeeze it out into low-level code. Now, what's the quality of that low-level code? Is all low-level code created equal? Does every one of you in here write equivalent quality programs in high-level code? In our power tools. Let's take this away from programming and just say, Nick and I here, we work on my boat together fairly often, and that's a euphemism.
No, I work on the boat.
Okay, so what's the punchline there? He has a lot more experience with that stuff than I do. So we can both be using the same power tool, yet he's going to get more than likely a much more polished result with whatever he's doing than me because he has experience doing it. And vice versa, I like my chances in computer programming over Nick. Okay, okay. But the punchline is that, at the high level coding example, we're not necessarily all created equal. We have different experience levels and things like that. Who's in charge of the quality of that low level language? What's the tool that produces that low level language? Compiler. Are all compilers created equal? Are compilers perfect programs? Are they perfect programs that always produce perfect low-level code?
They're not you.
Or do you? Yeah. I mean, I'm probably the only person in here who's never written a bug into their code. Any bugs that exist in my code pre-existed in the language itself. All right. So, punchline is, could we probably all agree that the earliest compilers produced crappier low-level code than the modern compilers? We've improved. Those compilers have become better and better and better and produce more optimized, whatever. It turns our garbage high-level code into pristine-ish low-level code, right? Right? So at what point in time would a human being actually have to step in and modify the low-level code? It happens less and less often today. Let's go back 15 years. Let's look at our video games 15 years ago. It's not that it wouldn't happen today, but it's going to be less common today. And let's say we have a part of a video game that just absolutely needs to be really, 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 really fast. Okay? Now, we've all experienced as we're writing code for different things that sometimes we have to do something in a high-level language because Java or C# will scream at us if we don't. We have to check to see if a value is null before we actually are allowed to use the value. Swift is the worst at this, right? Those of you who are in the Apple Watch class. Swift wants us to unwrap things and use optionals all over the place. Like, look, I know this will never be null. Just trust me on this. All right? But we have to still wrap it in if statements and things like that. So what's the compiler going to do? The compiler is going to have to create an equivalent conditional at the low-level language perspective. Now, as a human being, we might say, you know what? This part of the code needs to be really, really, really fast. And I happen to know that this condition that we were forced to check for technically cannot happen. Compiler couldn't have known that. Okay? We were forced into writing this in the high-level language because that's how the language was built. Okay? But I'm going to go and I'm going to remove some of these checks because they're frivolous. Frivolous checks. Okay, we don't need to ask if this is null or any of this stuff because I know it won't be. I don't want to waste time in this particular part of the video game having it ask all these extra questions.
That's how you get trapped in the vault.
What's it?
So that's how you get trapped in the vault.
Trapped in the vault.
Yeah. On Fallout.
Oh.
You get trapped in the vault. Remove too many lines of code.
That's in the you mean the vault you start off in?
Yeah. Well,
Oh.
I mean, if you did what I did on the game already and mod it a lot.
Why would you mod a brand new game?
Because I built my own city and armor and guns.
All right, well, I need somebody to build me some cores so I don't have to go and find them for my suit. I also need infinite bullets.
I have a stash of.
I need infinite bullets too.
Console commands.
Huh?
Console commands.
I haven't even. I know of what you speak. I saw the preview stuff.
Yeah, you just tilt the key and you get it right away. You don't have to do any options or anything.
Oh, you can just cheat?
Yeah.
Oh, that's awesome. That's awesome. I love cheating at video games. All right. So punchline here is that sometimes as a human being, it might benefit us to go down to the low-level language and clean it up a little bit where it's less, quote, foolproof, but in the context of the problem we're actually solving right then and there, we know we can remove some of those things, those checks, and speed it up, right? Okay. Are there equivalent examples to that in our operating systems? I mean, isn't a video game kind of like an operating system in and of itself? Some parts of it we're not going to notice whether it was efficiently written or not. Other parts of it, when a lot of stuff is happening, we are going to notice. What part of an operating system that we've discussed needs to be really, 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 really fast? Okay. booting part? Tell me more about that. I think you're wrong, but let's go with this. Okay, does that have to be really, really fast?
Well, I don't wanna sit here and wait.
You don't want to, but is it a make or break thing? If your operating system boots in 13 seconds instead of 8 seconds, has life changed
I'm
for?
like talking like back in the day where it would take 10 minutes for me to start up my computer.
Okay, fine. So then that's a good reason not to shut down your computer.
Just let it run hot. Add
Yeah,
those
just
extra
leave it on.
fans.
Once it's started up once, you leave it on. Just like Android developers, never
Hey,
have never shut down your emulator.
But,
What if I have to, like restart for an update or something.
oh,
Well, hopefully you're not present for that. It restarts in the middle of the night.
well, you might have an issue there, like lighting a dorm room on fire.
Well, that was overclocking. That was a different situation.
It's still-
So what else? What needs to be really fast that we've talked about recently?
Programs, switching between them and
Schedulers, right? So we have our short term, we have our long term scheduler. Okay, long term scheduler. If that guy's a little bit hit, he has an off day, not the end of the world. His job is just to keep those queues filled, right? But the short term scheduler, the dude who literally delivers a PCB to the CPU, he's got to be pretty quick, right? Because we already have the slowdown in context switching, right? I mean that's the built-in evil. Can't get around it. All right. We need him to at least get the thing into the system as quickly as possible so that slowdown, that slow context switching can start. So are we going to do fancy schmancy stuff with that? Or are we going to try to cut out all the extra stuff so that he can just do what he does quickly? We want it to be fast, right? Okay, so remote procedure calls, when we have something that tells the short-term scheduler that it's now time to do something. You know, we have all these little pieces mechanically working together. So we have one dude who kind of like shovels coal out of the queue and throws it into the CPU, right? His job is to take the next highest priority PCB, throw it into the CPU, and let the context switchy thing happen, right? Okay, well, somebody has to tell him that it's time for that to happen. So we have, the foreman who's in charge of the CPU is going to be up there and says, okay, this guy's out of here, whether his time ran out or he just got an interrupt because he has to go and, go into the wait queue, the device queue, whatever you want to call it. For some reason, this dude might be done on the CPU. And now we need to notify the short-term scheduler that we need another dude. This guy's done. And every CPU cycle we wait is lost performance on the system. Okay, we already know we have built-in lost performance from context switching, so let's go ahead and let's minimize additional lost performance. All right, we don't need fancy tools to get to make that happen. Within the operating system itself, would you expect to find, at some point we'll look at the source code for Linux, but within the operating system itself, would we expect to find easy to read code or pretty scary looking complexy type code? More of the latter, maybe? Not that there's an excuse for writing bad programs. There's a Levi posted on Slack the other day about Linus Torvalds, right? A guy who manages the Linux source code, complaining about bad programming. So certainly we want to still have good programming practice in that, but we're probably not going to see really, really, really well written, well organized code, okay? Because we're kind of building on code that's been around since the 1960s, okay? And you can only duct tape stuff so much and make it look pretty, right? So we'd expect the operating system source code to look scary to some extent, correct? So one of our goals is not to pretty this thing up and have everything in nice little modules and stuff like that. In fact, like we talked about with remote procedure calls, sometimes that prettiness leads to some performance issues, okay? Especially when we don't have standards. Wouldn't we agree that today we look at other parts of technology that standards is what drives things? If we have a standardized way of doing something, that tends to prevail. If we have a proprietary way of doing something, it doesn't work out so well, especially in modern computing. Before USB, we had 40 different ways of hooking a mouse into your computer. All right, and sometimes you wouldn't have the right adapter. You'd go get a new mouse, and it would have the wrong number of pins to fit into the plug in the back of the thing. And sometimes you bend pins, right? If you're bending something with USB, you're pushing too hard. is what's is what's happening. But punchline is we're used to standards now, and everything that we do involves these standards, and there isn't a standard for remote procedure calls, which probably led to it not being used very often. Okay, so let's jump down here. We talked about direct versus indirect communication. So this is kind of that idea of message passing versus shared memory. Do we talk directly to another running process, or are we talking indirectly to that running process through shared memory? Synchronization. So now we have multiple processes floating around in the operating system, and these guys need to be on the same page for some reason, and we'll talk about that more here in Chapter 4 with threads. Okay, but we need to have mechanisms for making sure multiple processes are on the same page. Okay, and we're going to talk about that in a micro example through threads. Because threads are managed by their parent PCB, right? So we can look at that. How does the parent PCB manage all of his little worker bees that he's in charge of? Instead of looking at it at the entire operating system level, where we have 300 running processes, 300 jobs in the queues, and how do these guys stay, how do the small subsets of these guys stay on the same page at the operating system level? Okay, harder job there. Talked about buffering. Here's POSIX is one of our standardized things, so this is exactly what we're talking about here. So there are standardized ways of getting shared memory. There's also standardized ways of using mailboxes for message passing. There are not standardized ways for doing remote procedure calls. Doesn't exist. All right. Well, unless you talk to Solaris or you talk to the makers of Windows and they say, oh yeah, our way is the way. So our library for remote procedure calls works great as long as you're running Windows. Kind of like they say .NET's platform independent, like Java. Runs on any platform as long as it's Windows. Okay, because it runs inside the .NET component architecture. Okay, so let's keep flipping through here. Here's the local procedure call versus remote procedure call. Talked about that. All right, so this is the stuff we were talking about right at the end of last time, and here's the remote method invocation stuff I was talking about with Java. So let's just pretend like that's dead to us right now. Interesting idea, might come full circle at some future point in time, but right now wasn't well implemented. So we really care about these two things, sockets and pipes. Okay, so sockets and pipes are kind of our predominant ways for processes to directly communicate with each other. Okay, sockets would be our general purpose way that's network aware.
Do those pipes go into the socket?
Directly, yes. All right, so the idea here is that a socket takes into consideration that the internet exists. Right, so now we can have processes that run on multiple operating systems, whole different memory architectures, talking to each other through some sort of communication channel. This is the cans with the strings between them. All right, and that's our that's what a socket is. A pipe is a local only version of that. All right, so we talked a little bit about this last time. There's kind of two pieces to a socket. We have an IP address which uniquely identifies a machine, and then we have a port on that machine. And most of our modern operating systems have support up to 65,536 unique ports, which is a 16-bit unsigned integer. So same thing as Java chars in terms of size. But the reality is the first 1,024 of those are reserved by the operating system for operating system specific stuff. So if you're writing your own program, which we'll do at some point, we'll have some sockets talking to each other, you would operate on a port above 1,024. But at the end of the day, it's I want to talk to this computer on this port, and the idea would be there's another program, there's a process running on that computer, on that operating system, listening on that port. And that's how we establish that communication channel with sockets. All right, so here's a nice little picture with a dinosaur on there. Okay. Let's see. Remote procedure calls, they're dead to us. The stubs, if you guys read about this, this is the this is kind of like an old C, the old C programming language where you could write kind of a prototype for your function. It's not the actual implementation, it's just what it looks like so we know how to call it. So you'd have to have all your stubs over on the client side, and you actually have the implementation over on the server side or on the receiver side, and then you can actually make those calls. It was really a stupid implementation. All right, so pipes are the more interesting thing. So these allow two processes running on the same system. There is a such thing as a remote pipe. This was actually like the predecessor to sockets. They don't exist anymore because sockets are now the way you have two programs that are sitting on different machines. That's how they talk to each other. But a pipe would be a communication channel sitting between two processes on an individual computer. Okay, and pipes come in two forms. Okay, we have named pipes and we have unnamed pipes. Okay, named pipes are more bestest. Okay, they're better than unnamed pipes. So named pipes give us full control over that particular communication channel, and they're also bidirectional. So we use a named pipe whenever two processes need to send information back and forth between themselves. So it is message passing, but this is a mechanism for message passing. It's like one process making a phone call to another process, but leaving that communication channel open and also putting a little post-it note on it saying, this is who I'm talking about on here. This is a named pipe. Okay? So whenever I need to talk to Fred, I'm going to pick up this phone. Fred's on the other end. Okay? That's our named pipes. Unnamed pipes are just generic ways of letting the other person, who we might not know who that is, the other process, know about stuff. Okay, so ordinary pipes allow communication in a standard producer-consumer thing. That's our process and sub-process example. So processes spin off other processes. So producer writes to one end of the pipe. Consumer reads from that end. Ordinary pipes are therefore unidirectional. So unnamed pipes can only receive things in one direction, as opposed to named pipes can send stuff back and forth. Okay, and this guy requires a parent-child relationship between the communicating processes. So the idea would be a parent would fork a child, okay, in the creepiest way possible.
And then show
Okay. Okay, and then what would happen is a unnamed pipe, or what the book's calling an ordinary pipe, would be established, okay, between the parent process and the newly created child process.
only when the child misbehaves.
Correct. Okay, and now that communication link is available, but it's only within the producer-consumer problem that we briefly talked about before. That is, the parent can send data to the child, but the child cannot talk back to the parent through this automatically established pipe. Make sense? If it needs to be two-way communication, now we need to create a special purpose pipe and name it. Okay, hand the child the walkie-talkie, parent has the walkie-talkie, and now they can talk back and forth. Okay, go ahead.
So is it an ordinary pipe is it synonymous with unnamed pipes, or is it just
Yes.
a type of unnamed?
Yeah, it's synonymous with it. Yeah, unnamed pipe we don't have a special phrase for it. It's the generic pipe is an ordinary pipe, which is also an unnamed pipe. Specialty pipes would have our named pipes, so they're usually called named pipes. I've always referred to them as named and unnamed, but I've also always called the device queue the waiting queue. So, of course, my way is correct and the book is wrong.
But the book has dinosaurs.
The book has dinosaurs. How can it be wrong? All right, so yeah, this is basically the stuff we just talked about. So this is the pipe. We have a parent, we have the child, and the parent can send information to the child and whatever. All right, so here's our named pipe. So more powerful than our ordinary pipe. So that's, like I said, more bestest, right? So more powerful. Communication is bidirectional. So these are like walkie-talkies or a telephone, whatever. Pick your poison. We do not have to have a parent-child relationship. When a parent spawns off a child process, a unnamed pipe is automatically formed. There is a link between a child process and the parent. And we saw this when we wrote our little simulation for processes being born. We haven't actually implemented a PCB spawning off another PCB. We've talked about it. But when we wrote our long-term scheduler creating a PCB, we let the PCB know who its parent was, right? We probably think we passed in null for that. That way, a PCB knew it was the top level process if its parent was null. If its parent was null, that means it was born from the long-term scheduler or the process scheduler, as opposed to the CPU scheduler. Now, if a PCB or a process spawns off a child process, that child process becomes aware of its parent. It knows the process ID of its parent process. That makes sense? And this pipe is the mechanism by which it can receive stuff from the parent. All right, so homework assignment is up. Finish chapter 3. Look at that. All right, so we'll start chapter 4 next time, which is on threads. So we're going to rip through that pretty quickly, do a couple little examples, then we'll update our simulation that we've been working on to make it multi-threaded on the CPU. All right, I will see everybody on Friday.